Okay, we're back at the room. So I'd like to introduce the next session with our first speaker is Dave Wagner, the group supervisor of the modeling and methodology group at JPL, who will be talking to us about the value of ontological modeling, um, giving the example of an engineering application about harness design that we have developed at GPL using the Open Caesar framework. And after that, we will have a talk from Steve Jenkins, who will be talking also about the value of ontological modeling, especially to manage the supply chain. And then we will have Yuta giving a talk about their experience at JAXA of using ontological modeling so far. Okay, with the first speaker, Dave, please go ahead.
Thanks, Megan. Everyone hear me? That is a yes. All right, so I chose this topic of harness design because this was our original Caesar, Open Caesar application, the Caesar application that we developed to help specify harness design for Europa Clipper preceded Open Caesar and preceded OML, in fact. So this is a fairly mature application now. It's kind of in its third generation. But this is also a good example of an application where we are using this specifically to integrate an ecosystem, a pipeline of applications, and it's talk about what works and what doesn't work, how to connect those applications. So for those of you who don't know, spacecraft are robots that have a lot of electrical parts that have to be connected by electrical harness. The thing that kind of distinguishes electrical harness, we were talking about this at lunch, electrical harness is kind of the same thing in spacecraft and in cars and in airplanes. But the thing that distinguishes it from a system engineering point of view is that on spacecraft, it first of all represents a sizable chunk, about 15% of the total mass. It's kind of the last thing that we can specify in the system design, because figuring out what needs to be connected requires that you know what needs to be connected, and it's all those other assemblies that you're trying to figure out in architecting. Okay, so it's kind of the last thing. You can't design the harness until you have designed everything else. So it's the last thing that we can design, but it's the first thing that you need in ATLO before you can start testing it. Okay, so it's a critical path driver on the entire process. All right. A spacecraft like Europa Clipper can have tens of thousands of wires, thousands of different kinds of signals. And it's complicated by the fact that we're having to integrate instruments from lots of external institutions with JPL avionics, or sometimes contracted out avionics. So it's complicated. And there are many different patterns of connectivity that have to be accounted for. We have, well, let me just go to the next slide and talk about how this fits into a larger tool chain. We used to do this all on paper. It took a long time. It took a huge amount of human effort to do that. Untold amounts of paper. Okay. Over the last 10, 15 years, we have adopted an electrical CAD design tool that we use to do most of the electrical design. use a Siemens product. And it's capturing this kind of middle box in this picture, where we can start with a logical design. What are the things, what are the signals that need to be delivered from box A to box B? It models a topological view of that. Where do these wires need to be routed to get from A to B? Okay. And then down to a wiring level view that actually looks at, individual wire cores, what wire treatments are needed, how they different kinds of physical connectors. That's already provided by this commercial product, and we love it. That's great. It's a huge amount of effort that still goes into doing that level of detailed design. On the right side, this connects to other models, though, because in order to do the topological layer to understand where the wires need to be routed, we connect to a mechanical CAD model that knows where the boxes are going to be on the spacecraft, where the structure is going to be, how the wires have to be routed around things to get from one place to the next. Knowing the routing is important because the length of the wires, Ohm's law determines, how thick the wires have to be in order to carry a certain amount of current. So we have one external CAD model that we use just to figure out the wire routing, and then there's another physical design that the output of this electrical model feeds into a mechanical CAD model where they actually design the harness. Okay, and that goes into the fabrication. There's another model that comes out of this that kind of reflects a graphical view of the ultimate wiring design. And we did that because, first of all, JPL has a particular way that they like to see these electrical wiring. But also because we didn't want to have to get a license or capital for every user who wants to see those wiring diagrams. So we actually export the model in an open form that describes the wiring in a way that we can project it through this web-based tool called Elvis. We actually paid to have that thing developed, and then Siemens bought it, so now it's all part of Siemens. Okay. But that allows the people who are down in Atlo assembling the spacecraft to project wiring diagram on a big screen, and they can see which pin are we connecting here. The focus of our work was on the left side of that process. And we wanted that we were working with the engineers who actually at JPL, we have systems engineers who are supposed to be responsible for specifying the requirements, what needs to get connected. Another group of people who are responsible for doing the detailed electrical design. They frequently cross-pollinate and share each other's jobs, small teams, and it's a lot of work. They needed a solution to help them specify the requirements for what harness needs to be built. They were doing it with spreadsheets. They found that spreadsheets were not very precise. They weren't really sure what they wanted to say in those things. They were kind of trying to capture the design in spreadsheets, and then very ineffective. So this is where we came in, helped them develop a model, vocabulary, to specify these connections. And this was the Caesar application. And Mag had already showed you earlier in his presentation a brief demo of what the Caesar user interface looks like. We very carefully considered that we wanted to keep the look and feel of the spreadsheet used to. Wanted to capture the model in a precise ontological formulation so that we could precisely extract the specifications. And initially, we turned those into printed reports that they could interpret in the design. We have since then actually automated that connection. So this is a case where we now have a completely automated transfer of information from our Caesar model into the CAD model. It doesn't actually generate the design yet. That was a goal, much harder than it sounds. But we do have the ability to at least connect that information automatically into Capital. Capital can import the information. The designer can see, here are the requirements for this function. And then they can do the electrical modeling. What I just showed is part of an even larger pipeline where the people who are doing these specifications kind of have to get their information from somewhere. This is something that we're still working on, and I'm actually going to come back to this slide a little bit to talk a little bit more about some of these other connections that we're thinking about. But first, I want to talk a little bit about what we captured in this set of models. So when we think about specifying the connections, initially we were thinking in terms of, well, thinking very close to the level of the topology of harness. Oh, where does the wire need to go? What circuits does it need to connect, and what does it need to go through to get there? We need to think about kind of supply and demand. This is the best way to think about it. There are things that need power, so you need to figure out how to get the power to that thing. There are things that produce sensor data. We need to figure out how to get that data to. Think of it in terms of supply and demand. The people who were thinking about this way before us were thinking about this in terms of functions, but they're really thinking about functions in terms of signal connections. Okay, that needs to translate down into and then we're thinking about interfaces at the top level. What are the not just the things that need to be connected, but specifically what are the kinds of signals and where do we actually get that information from that box? When you think about the electrical level, those interfaces quickly become physical connectors. But at the level of system engineering, we don't really want to be thinking about physical connectors. Really rather be thinking about the signal, the purpose of the function. And so we modeled it in terms of what we call end circuits, which is we're looking past the black box into the component and saying, what is the function inside that I need to connect to this outside? Okay, with really simple parts like simple sensors, the part is effectively same thing for a heater. But for a lot of other things, have a lot of analog to digital converters that the box might have 100 different channels that it exposes, interfaces. What the system engineer wants to think about is what channel it's connecting to, not what connector. They don't care about the plug. Okay, so that required a little bit of new vocabulary to think about end circuits rather than physical connectors. And then, there are all these other concepts that come in down at the level of wire. Things like field joints and wire treatments and how you bundle the wires into harnesses. Fortunately, most of this vocabulary in the middle here was already provided by, you didn't have to invent that. Already there. It was already common vocabulary in electrical engineering. We just had to understand what does it mean and how does our level of specification need to relate to that. And one of the things that we realized was we don't really want to be talking directly in terms of things like wire gauge. Okay. Of course, in the first version of Caesar, that's exactly what we did, because that's what we were told. That's what the customer asked for. But we quickly realized that if we actually specify at that level, if we make the requirement, this wire has to be this particular gauge, then every time they change the design, we have to change the specification. Okay. So it's important to remember what we're modeling here is specification level. What the requirement is, that wire needs to carry a certain amount of current, right? So we changed the vocabulary to be more specification oriented. This was an evolution that happened over time. But now it's gotten to the point where our specification models are very stable, as requirements should be, where the design can change out from under us and we don't care. As long as it's still satisfying specification, fine. The vocabulary that I'm talking about is all, almost all of it in open source, in OpenCaesar. And you'll see that there's all kinds of concepts and relations in those vocabularies. But ultimately, this pattern is where 90% of our model ended up. Okay, that components can present interfaces. And then we have this concept of a junction that can join interfaces. We specialize that in Caesar to say that we only care about hardware components. Okay, we call them, our customer wants to call them assemblies, so we call them assemblies. Like I said, we model end circuit interfaces to distinguish those from physical connectors. And then we have this concept of a function, which is specifying connections between those end circuit interfaces. It's important to point out that function here is a concept. It's a thing, not just a relation. And we kind of came to that realization fairly quickly because not all connections are binary. We have things like power buses that need to connect multiple different interfaces. Okay. So, and also these functions need to have properties of their own, because the function is really the subject of this model. Main subject of this model is it need to connect these things. That's the function. The function has these properties, like it needs to carry a certain amount of current, or this is a data interface, RS-22 versus a power connection. So that needed to be an object so that we could actually give it properties, and it needed to be a single thing rather than a sequence of connections between things, because we want to be able to query this model and say, tell me what the list of functions is. Tell me what end circuits each function joins. That's the primary purpose of the model. The next thing.
You said you only did it with actual hardware stuff, like you did your software aspects a little differently than this, or did you just
I'll get to that.
Okay.
So then we specialize these types to have a library of different concrete types that our users can relate to. And that allows us to also create prototype templates for these things where, you know, a battery presents a particular set of end circuit interface. Okay? A battery has a power interface that can go out, or you know, an A to D converter has some number of analog input interfaces, things like that. This is just showing kind of the top level of that. The libraries that we're actually using right now have dozens of different specialized types, and we specialize these down to this is the actual kind of assembly that we're going to be using for power switching. This is the actual kind of computer that we're going to be using, so that the users can just kind of pull those in off the shelf. Okay, that way the users don't really need to think about how do I model, you know, what interfaces this box presents. They don't have to worry about those details. Do that for them. And then we also have specialized types for all of the different function types. So a power connection versus an RS-22 connection. And that allows the Caesar tool to help out the users by only allowing you to specify compatible connections. If this is a power function, you can only connect it to power end circuits. You can't accidentally connect a power function to an RS-22 port. And that helped us eliminate a huge category of typical modeling mistakes. Okay. This similar level of high-level types also maps perfectly well into the vocabulary that was already provided in the Capital tool. Like I said, we don't actually model this, Capital models this, but it still works perfectly well, just to suggest, you know, that that's a, there's a reason why that's here, and it's the same pattern in SysML. So I did want to go back to this picture. There was a question about software interfaces. We built this primarily to specify hardware, to specify harness, and then we realized that, well, gosh, you know, that pattern works pretty well for software too. And in fact, even this pattern of what connects to what is something that our software needs to know about, because if we have a electrical connection that delivers power from this power switch to this instrument, well, I need to close that switch in order to power that device. Okay. And so it was a very small step to go from here to add a few more properties, talk about how do I address that switch, to give the software people another specification that says, here's how to control that switch. Here's how to control, you know, the power on that device. Here's another data set that says, here's the mapping from a particular sensor, knows what it is. You know, it's measuring the temperature of something over to this A to D port, which tells you what your telemetry channel is going to be. So it was a very small step to go from modeling harness to modeling software interfaces. I do have to say, though, that because this was initially focused on modeling harness, we realized that there were some electrical functions that exist as electrical connections, but they don't require harness. For example, we have connections that go to the backplane. There are other connections like grounding connections, chassis, go through mechanical parts. So it's not perfect yet. There are still a few loose ends like this that we have to deal with. In the case of those connections that go through chassis or backplane, the pattern still works. We just now have to convince people you need to also include these functions in your model, even though they don't harness. So now we actually have to add a property to the functions that say, these functions you actually need to build harness for versus these you don't. I don't want to say everything, okay? It works for harness specification, and now demonstrated that it works for software specification, okay? And in both cases, we have a pattern like this where we are producing a product out of Caesar that the downstream tool can directly interpret. In case of software, they actually directly translate the JSON product that we deliver. They translate it directly into C++ code in the flight software. Okay. I mentioned also earlier that.
Hey, Dave.
Hi, Steve.
Yeah, hey, I just would also mention that Caesar was not originally designed to do harness either. It was designed to do systems engineering, and it was an adaptation to add harness to it, even though it was the sort of the first flagship application. But it was already a veneer of a new application layered on top of a very general engine, and then extending it even further is just the way it was designed.
That's a good point. The first application that we actually built with Caesar was a mass management Bell roll-up tool where we only had the components to deal with. Okay. But we took that exact model of the composition and just added functions to it. So we added the interfaces. And Steve had a lot to do with that, by the way. The last point I wanted to make here is that we're kind of now looking at where does the information come from to go into Caesar first place. A lot of the detailed information comes from these interface control documents that describe the actual interfaces of the hardware components. The problem with using those as a source of information is that ICDs are always the last thing that gets delivered. So using them in this process is hugely problematic because the information is just never there in time for us to build these specifications. So system engineers tend to rely on this, what we call a system block diagram, which tends to be something that they do in PowerPoint or Visio to kind of sketch out, here's how I think the system is supposed to work. And then they will translate that into the model. It'll go down into design. They'll find all the problems, come back up, and sketch it out again, system level. People have realized now that that's not very efficient either. We probably need a higher level of model to capture that information graphically. And now we're talking about doing that either in SysML or directly in Caesar. So in Caesar, once you get the information in there, we can render it graphically, turn it into that graphical form. But Caesar, we tend to be modeling at the level of every individual function. So if we have 800 temperature sensors, you're going to have 800 functions. Whereas the systems engineers tend to like to think of those things a little bit more abstractly. They like to think, okay, there are going to be some temperature sensors. We'll just sketch that out as one line and say times 800. That's the kind of thing that you probably could do in SysML. If you had to do the 800, that would become a little bit tedious to do in SysML, although we could. In fact, Siemens demonstrated to us a couple weeks ago that they have their own product now that will translate from a SysML model directly into the capital design. But but it requires you to model with their patterns in SysML, and it requires you to model in SysML, which our systems engineers would probably just not do. Okay. But if it was just a matter of sketching out the design, SysML, we could probably do that. Okay. So that's kind of one of the things that we're looking at right now. As we transition to SysML v2, I think it's entirely likely that this pattern that we have modeled in Caesar will eventually get translated into SysML, and we'll probably be doing it in SysML. But the thing that makes it really easy for users to use right now is the fact that we have the libraries, and the fact that we have a wizard that helps the users construct 800 instances of the same kind of connection with one click, right? Rather than have to click out 800 dots and lines. So that's all I have. Any questions?
There was just one question in chat. I think Steve responded, but if you'd like to comment, the question is, what are the categories of mistakes this approach solved or like helped capture?
Right. So the biggest category of mistakes, and this was particularly applicable to the software interfaces, was just incomplete connections, incomplete connectivity. We can easily query the model and find interfaces that are not joined, or we can find partially joined functions. So we can find a function that says, you know, you've connected a function to a demand, a load, but you haven't actually joined it to a source. Okay. And we actually produce, as one of the reports, an incomplete functions list. This is, you know, all the functions that we found that you've either, you know, violated that pattern. And that was hugely useful to the systems engineers to help them develop a complete and consistent specification.
Thank you so much, Dave. And we will be transitioning to our next speaking in the session, Steve Jenkins, former JPLer and currently consultant in the area of ontological modeling and analysis. I'll just give me a second to stop and start recording, right?